So we are ready to start with E4S. And Todd gave a very good overview of the different technologies that we are developing in the scale computing project. And we heard from Andrew about containers, and Dave gave us an overview of how all this will work on our facilities. So I want to describe what we have currently and where we are going. Our goal is to produce these packages on multiple platforms in a way that you can easily download through build caches, through mirrors, where you can get optimized binaries for a variety of different ECP/ST tools, and you will be able to easily deploy them on your platforms using SPAC. You will be also able to deploy the software using container environments, and I'm going to describe our efforts in the Extreme Scale Scientific Software Stack, or E4S project. So E4S is a community effort to provide the open source packages that are being developed by ECP and other developers on HPC platforms. So we provide both source-based builds as well as containers for a broad range of HPC software packages. And our goal is to accelerate the development, deployment, and use of this HPC software and lower the barrier for HPC users. So we have containers and from source builds of many HPC packages. These include runtimes like MPI, which includes MPICH and OpenMPI. It includes development tools such as the Tao Performance System, HPC Toolkit, and PAPI. It includes math libraries like PETC and Trilinos. It includes data and visualization tools. And this is the software stack that will help you deploy many of these packages. We use SPAC as the primary means for software development and delivery. And we use SDKs, which are a collection of related ECP/ST products, where coordination between these packages improves usability and practices. It also fosters community growth among teams that develop these packages and develop similar and complementary capabilities. An SDK typically involves many related packages under a single umbrella. And we have containers with pre-built binaries of ECP/ST products. We also support a variety of different runtimes. We support the Docker container environment. We support Charlie Cloud, Shifter, Singularity, and most recently we have also supported Inception at NCAR, where we showed a demo of E4S, and it's supported by the system staff as one of the options that you can choose when you run your jobs at NCAR. We also have an OVA file, a virtualization appliance that you can use with VirtualBox that contains all of these runtimes, and also it contains the ECP E4S image in a Singularity container. So we have a USB stick here, as well as you can download all of this, all of these packages from our E4S.io website. So if you would like to try some of these environments on your own laptop and you have enough disk space, I would say at least 35 GB, please talk to me and I'll give you this USB stick, and we can install everything locally, and you'll have an environment that you could use on HPC systems as well as on your laptop. Okay, just a show of hands, how many people here would like to try that in the hands-on? Okay, so we have a couple of people here.
You could just Docker pull it.
Yeah, you can Docker pull it, exactly. So there's a Docker Hub image over here, and you can just do that.
Start your pull now.
Yes. And I would like to spend some time, Todd already mentioned about MPI replacement strategies and we heard a little bit about that, but I would like to show it in action and try and build an application locally, move it to Frontera and run it on a couple of nodes over there. Okay. So as I mentioned, the basis for all the software delivery in ECP is SPAC, and E4S uses the SPAC package manager, and it allows you to specify different versions of packages, as you saw. With the E4S container image, you will be able to use SPAC on Frontera or on your laptops and get a feel for using multiple packages. Now, SPAC is the basis for the software delivery, and it simplifies HPC software for users, developers, cluster installation, and the largest HPC facilities. And it's central to our software strategy. The roadmap is packed with new features for SPAC, including ECP software distribution, build pipelines. We are looking at workflows for building containers, stacks for facilities, and chains for rapid development workflows, optimized binaries for different platforms, and better dependency resolution. You can find out more about it over here. Now, I just want to show you some hands-on examples for how you use Docker. So you can just use Docker pull with that URL, and then just if you're using the USB stick, you can just unzip this and load it in Docker. Look at the Docker images, mount it like this, and get a bash shell, and then you are in the container. And what's important to remember here is that we are not using a virtualization layer. There is only one operating system, and you're running the Docker environment on your laptop, and then you can just copy up some of the demo examples, and maybe I'll show you some of these. Now, E4S second release that we did in January has a number of packages. We have over 37 packages. You can see the paths where they're installed. And I'll not go into the details of this, but I just want to say that if you say the SPAC find, you will see all the packages that it includes. And these are full-featured packages. Like just looking at Trilinos, if you look at the lib directory, you'll find all of these solvers that are included in the container. So one of the issues that was raised is, how do you run an application that you built on your, say, laptop on an HPC site? What we would ideally like to do is not use the MPH, which is within the container, but replace that MPI with the system MPI. So if you replace the MPI in the container with the system MPI, this will allow you to use the fast internode communication network, the native interconnect, and you can mount the data and the application in the container and then use the programming model, libraries, runtimes, compilers, and tools from within the container. By replacing this MPI using the MPICH ABI compatibility layer. Now, Todd spoke a bit about API and ABIs in his talk, and we are now targeting the ABI layer for MPICH replacement. And our goal here is, can we build a binary on one platform and have it run on all the HPC platforms, whether they are a Cray platform with Aries interconnect, or whether you have a Mellanox InfiniBand system, or a laptop? Can you take a single binary and with the help of the container, run it everywhere for an x86-64 system? Now that's an interesting proposition, because until now, our MPI applications are exclusively distributed in source form, right? You have source starballs. But what if you were able to distribute a single binary and tell the users, download this container and run this command, even if that command is a little long. If you could just say, just run this script, and you will be able to replace the MPI in my application with the system MPI. So you will get the fast internode communication, and you will be able to run it on all these systems. So that may be a good way to demo the software in the future. So we all have these accounts. I would like to thank TAC for giving us access to their new Frontera system, which is currently the number 5 system on the top 500 list. And we will all be able to use the E4S container on Frontera. Is there anybody here who has not filled out this form or who doesn't have the form? Well,
yes, we have the form.
you have the form. Okay, that's fine. You can give it to me later. That's fine. So I would like to show this demo to you, and just an example of how you could use MPI over there. So to get an interactive node, you can say idev-m and some time in minutes, say 50 minutes, or you can say idev-m 50-N2s to get 2 nodes. And you can load the Singularity module. You can run this command and get a bash shell. You can build and you can run your application. Okay, and this is the application. And what we do here is we want to use the system MPI, and to do that, what we are doing here is we are replacing the mpage in the container with the mVAPage 2.3.1 from this location. Please let me know if you have any problems with permissions or errors with this. But what we have done is we have mounted in Singularity the etc libib hearts directory in the container. We have also mounted the system user lib64 as host lib64 and put it in the LD library path along with the libib hearts directory, and then we can run the application. You can also build an image and run it on Frontera like this. You can just copy an example, you can build it and compile it and run locally, or copy it to the Frontera system and run it over there with this N2 and try running this example. So let me just show you this on Frontera. Here I have done an idev-m in the interest of time. Are you able to connect to Frontera?
Yeah, I think on the demo directory there was permission denied and
on the demo directory? Now try that again. Okay. So what I'm doing here is I can say I've done an idev. Please do not run Singularity on the login node. I say module load tag Singularity like this. And so I can say which Singularity. Okay. Then I can say in my demo directory, there is a script called run singularity.sh. I'm just doing that. It launches a bash shell. So here you can see these messages, and now I have Singularity. It's running the E4S container image at this point, and you have the Singularity prompt. So here you can say which SPAC, and then say SPAC find, and then you can see all of these packages. Okay. SPAC location -I Trilinos will show you the location of Trilinos, for instance. If I say which MPI CC, it's the MPI is in my path. So I can build with this. So let me just go to NPB 3.1, do a make clean, and say make suite. Okay, just like in the slides. These slides are posted on the website in the agenda. And so you can see I'm compiling over here. It has created the lu.c.64, but mind you, I'm not going to run it from within the container because that would use the mpitch from within the container. I want to replace the MPI with the system MPI. Okay, and to do that, I will exit. So I'm out of Singularity at this stage. Now I'm back on the Frontera IDEV node, and I go to the next slide where I can cd to the bin directory, npb bin directory, and then cat the run.sh. Now note here in this run.sh, I'm first of all loading the Singularity module. Then I'm saying MPI run application, but I'm not saying MPI run LU. I'm saying MPI run Singularity exec the container. Okay, this is the ecp.simg image that Singularity runs. Singularity exec sets the LD library path, and then it runs the LU. So it gets dependencies from within the container, and then it replaces the MPI with the system MPI. You'll notice that it also has some mount commands where you say this directory on the host side is that directory within the container when I run that. And use the scratch file system over here as this and other things. Now we all recommend that we use the scratch file system while running any application. Okay, do not use that home directory. So we have mounted the op directory, we have used this. And here I can say run.sh, and then it will launch Singularity on all of those nodes, and we'll be able to run this LU application. Now, while it's doing this, let me just try and look at the other. Here it is running the application on two nodes. Instead of IDEV-M50, I had done IDEV-M50 minus N2, so I can get two nodes. And there it's successful, and I was able to replace the MPI. The next thing I'll try is, let me go to my laptop, and I have Docker installed locally. So I can say Docker images. So I have this image called Exascale Project SDK:AHM19, which comes from the all hands meeting we had in January. So I can say Docker run, and I will be able to specify this image. But before I do that, let me just mount my directory. Let me say users Samir should be mounted as, say, home Samir in the container. Then I say I want it to be in interactive mode, and then give a tag for the image. And the image name is Exascale Project /SDK:AHM19 and bin bash. Okay, so I'm saying, let me run bash command and do this on my laptop, on my MacBook Pro. And this will give me a prompt over here as Docker. Now I can go to home users, sorry, home Samir demo, which I have here, and say go to Trilinos, Zoltan. So I can say clean.sh. I can say compile.sh. All I'm doing is doing a make, but I'm getting Trilinos from that location. Now, in case you were wondering, I actually have SPAC in my path because I'm in the container. So this is no different from actually running it on Frontera as far as the installation. And I can say compile.sh. So I'm now compiling this Zoltan application with many of its dependencies over here. In case you are wondering what the dependencies are, here is the Zoltan. and here is the run. So you can see if I were to do this SPAC load of all of these packages like Trilinos, Hyper, Parmedis and all, then I can look at Zoltan and say LDD Zoltan, and it will show me what libraries it's using from within the container. Okay, and you can see all of these Trilinos coupling and Cicado. You can see there are quite a few dependencies, all these shared objects. If I want to see how many there are, LDD, Zoltan, there are 155 shared libraries that this application is using. So let me take this binary that I just built on my laptop, on my Mac, and move it to Frontera and get two nodes and run it by using two distinct nodes using the high-speed interconnect that we have over there. Maybe I should also try launching it locally on my laptop, just a few ranks to see how it does, because bad idea.
What? No, I didn't say that.
Okay.
Sorry.
So if I go to CD to demo app, Trilinos, Zoltan, and take this Zoltan here, and if I go to the Trilinos directory there, is there a Zoltan over there? Yeah, let me remove that. Okay. And take this and copy over my STP Zoltan to Frontera over there. Okay. I have this. Now I'll run it on two nodes. I've already got the IDEV-N2. Just saying that just put 16 on one and 16 on the other. So I'm running it on 32 cores. I'm again mounting the scratch directory. I'm mounting the opt directory. I'm using the mVAPitch2 that I have built here, and it uses the InfiniBand interconnect, and it runs it on two nodes. So I can take this run.sh and run it over there. So what I'm trying to show over here is that I could do the development on my laptop and have the full set of packages in my path and then run it on the system over there. Now, even if I were to try and run the same application locally, test passed. It took about, total time required was 11 seconds. Even if I don't do 16, if I do say 8 over here on my laptop, of course it will take a lot longer than the 11 seconds that it took over there. So I don't recommend that you run it on your laptop, but if you had a simple application, you could do something on your laptop in terms of development, and you could essentially, okay, so you can see it's going through its various parameters. So it is possible to do development on one machine and take the binary to another machine, and we have worked out the various issues with running it with different container environments and replacing MPI, whether it's using shifter on a Cray system or InfiniBand on a system like Frontera. So if you would like to have this development environment on your laptop, we have those images all on the USB stick that you can now use over here. And you can see it's going through its various parts. So again, thanks to TAC for giving us access to this really fast system. And having Singularity installed, which allows us to take this full ST stack and have it immediately available on a new system while they are working out the bare metal builds for various packages. The full environment is available and ready to use. If you wanted to try the Singularity command, you could just go and cd to your directory and say run singularity.sh like this. Okay. In the demo directory, run Singularity like this. And now you have the Singularity prompt, and you can verify that you have SPAC in your path and use SPAC and do all the things that you already learned yesterday with the various commands. And okay. Now Singularity mounts the packages directory as a read-only file system. So you may not be able to modify the user local packages directory because it's in a container, it's nailed down. But you can change whatever you want in the file systems that you have mounted. So you can then use your home directory and install things there, or compile the applications that you have over here and build it and run it. Like, for instance, if you wanted to look at this Trilinos example, you could go to the Zoltan directory and then you could say clean.sh and then say compile.sh, and it will build the same Zoltan example that I showed you over here. Just don't run it when you are in the Singularity prompt, okay? Because you want to be on the host side where you launch Singularity and launch the Zoltan application from there. So you should do an exit and go to the Trilinos directory, go to your Zoltan directory, and then say run.sh over here. And then you will be able to use the two nodes. So it's a good idea to, if you are trying this, do this with idev-m50 with the -n2, so you get two nodes. And then you can see the application running here. And there, it takes a lot longer for just the 8 over here. Okay. So any questions about what I just demonstrated? All the commands that I showed are here in these slides. Incidentally, if you are wondering where it spends its time in this Zoltan application, you can run this Zoltan application but use Tao to measure the performance of this code. Okay, all it needs is to say Tao exec-ebs module load Tao, and you will be able to generate. Sorry, I said run.sh. I should have said RT, which is run it with Tao. And so there are two nodes involved here. There's some communication going on. There is a lot of computation here. And you're trying to account for this time. And there are 155 shared objects that are being loaded by this. So if I just run it like this, I'm using Tao, which is not installed on the system, but it's installed in the container. So that's an example of using a tool to look at the performance of the same application. And there it is. At the end of this, it will create a single file called Tao Profile.xml, and it will contain the performance data that was captured in this execution. So I can, for example, here, I can just SCP from Frontera this particular file. And get it to my laptop where I can launch the Paraprof tool to look at the profile of the application. So this is the profile. It shows me it's running on these 32 cores. Here's the metadata for this rank. Here's the metadata for this rank. So do you see the host name over here? It says C101.212.frontera over here. Okay, this is for rank 0. And if you look at the rank 30, you see the host name is C101.213 instead of 212. So I know that it ran on 2 separate nodes over here. If I look at the rank 0 and say, show me the thread statistics table, it shows me the time spent in the application and all the MPI calls, like MPI barrier. I can actually go inside this MPI barrier and see the time spent in various MPI operations within this in the mVapage2 library. I can look inside the application and say, okay, it's spending about 8.6 seconds exclusively in the application outside of MPI calls, and sampling in Tao can explain 8.5 out of those 8.6 seconds. So it's close enough, and I can look inside and see where it spent 8.5 seconds. And if I just, it's saying that there is a routine called ePetra VBR matrix block row multiply, which is taking up 5.88 out of the 8.5 seconds. If I look at the other function, that is CSR matvec, ML chevy, and all the other matmult, matmult, and other functions, I did not need to change anything in this binary. All I said was tau exec -ebs zoltan, and then I can go inside this and actually see, say, show the bar plot and see the name of the line of source code, which says that this is an ePetra VBR matrix.cpp at line number 2342, where it is spending all this time in the ePetra VBR matrix block row multiply. So you can characterize the performance of your application and see exactly which ranks it's are spending how much time in each portion of your code. And this is an example of just using a tool that you didn't need to install because it was pre-installed in the container, and you can just run it from within the application like that, where you load a set of packages which all work together. And that's the central theme of E4S. These packages have been tested, validated, and they have a common integration point where all of them work together in this environment. And you can use the tools in a consistent way. There are several tools available in this distribution. There are tools like HPC Toolkit, Tao, PAPI, and others that are available in the container that you can deploy. Any questions about what we just saw on Frontera? Does that look okay? So even on a new system, you certainly have access to many different packages. If you are wondering about GPU usage, we also have in the Singularity image, if I say SPAC location-i CUDA, we have CUDA as part of the container, and you can use that with the container and other tools. So you have a very interesting set of packages that are available, and here's just a directory where you can see some of the tools over here, open blast and all, SPAC find, and you can look at the dependencies and the versions of packages that are installed. I should also mention that we have Miniconda 3 installed over here. So there is a set of ML AI tools which are already in your path. So you can just say Python import TensorFlow, and it's there in your path. We have Jupyter notebooks, we have TensorFlow, we have PyTorch, we have tools like Keras that are installed and ready to use. So this is a container that has many applications besides HPC workflows. We can use it for ML AI workflows where you don't need to install these packages. Sometimes getting this AI stack installed consistently and correctly can be a challenge on some systems where you want to have TensorFlow and PyTorch all in the same environment. So using the container, you have it all in your path, and you can try some of your other AI workloads on your system. And really, all you need is to have one of the 4 container runtimes installed on your machine. So with that, let me get back to my slides. And in the afternoon, I would encourage you all to try this hands-on yourself. Try these examples, compile the Zoltan application, launch it with this run.sh script. And remember, you can do the -n2 to get 2 nodes over there, and then run the application after you just compile it. I can go around the room later and assist you in case you have any issues with this. Now, we also have a VirtualBox image. And that VirtualBox image has SPAC pre-installed with many of the same packages in your path. Okay, so you can launch this VirtualBox image on your laptops. You can install VirtualBox and import the image. And with this OVA file, you'll see that we have Shifter, Singularity, Docker, Charlie Cloud in your path. So you can choose between different container runtimes, and then you can say also run one of the runtimes like with an alias. I have an alias called run SIF to launch Singularity, where you can launch the ecp.simg image and do the same example that I just showed you on my laptop, but within the OVA file. Are you comfortable with using VirtualBox images? Just show of hands, how many people here use VirtualBox? So a fair number of you have that probably installed on your machine. So you can just import that image and use it. Now we also have this image available on AWS. So this is the AMI ID, which is available in Oregon, US West 2 region. You can, of course, copy it to any region, like at the ISC tutorial, we just copied the image over to the Frankfurt region in Germany, and we were able to launch local instances on EC2. And AWS has given us a grant for research, and we thank them for that. And you can launch this EC2 instance. I can send you the login details. And then it's a free, royalty-free image. Anybody can use this on any number of AWS EC2 instances and use the AI HPC stack and the 4 container runtimes and launch your jobs. So this is an interesting option. Now I showed you how to do this MPI substitution with the Zoltan example. Here are some canned scripts for how to use it with a Cray environment. Now Cray has a module called cray mpich ABI, and we need to swap the regular cray mpich layer with the cray mpich ABI. This is how you would use it on ALCF theta system. You just swap the environments like this, set an environment variable like this, and say ap run Zoltan, but instead of ap run Zoltan, you would say ap run Singularity exec, this ecp.simg, load the packages that your application needs, set the LD library path, and then run Zoltan. This is how I would use the same exact binary on a system at LLNL, where I'm using mvaph2 and I'm using the system MPI over there. I'm just mounting the lib64 directory that this needs with the host lib64 over there and putting it in my LD library path and then running Zoltan after loading these packages. So this just shows that I'm able to run the same binary that I made on my laptop on a InfiniBand system at Livermore, the Frontera system, the Cray at ALCF, and also the Cray system at NERSC. This is how I use Shifter. Now, our image is already mounted over there, so you don't even need to load any image or download anything. It's just, you just say Shifter img images, and it will show you this image with the tag. When you say salloc to allocate your nodes, just say use this image of Exascale project SDK AHM19 to salloc, and then you can run this command. And again, Shifter will take care of some of the internal things about replacement, and you can just launch the application with Shifter, but load the other modules from within the container. So our future work, of course, involves increasing the number of ST packages that we support in E4S. We want to create this build pipeline so that you can build, test, deploy, and then create these mirrors over at the University of Oregon for E4S packages, so that if you were doing a bare metal install, you won't need to build from source. You could just take an image which will be signed by us, and you could just download the package in a binary form. It should be much faster than building the entire package. We also want to support the IBM Power 9 GPU system and the ARM platforms. That's in our roadmap. We want to support the GPUs better, visualization tools, and work out any kinks with the use of container runtimes with the visualization tools. We want to add the CI testing to our workflow. We want to help with the facility deployment. We are working closely with the Super Containers project for the scalable startup with full-featured super containers, as we call them, and improve the launch of MPI applications so it's not so ugly. You saw the script for the run, and I wish we had tools that simplified that workflow and didn't require the level of detail that is currently required to do the substitution of MPI and things like that. So we are working on that. In future tutorials, you might find that it's handled a little better, but there's a lot of work to do. And as we navigate this, what we are doing is we are creating recipes for building the SDKs. We are creating Docker build scripts that you can just do a git clone from our E4S site on GitHub. And you can then create customized images that are targeted to your application. So if your goal is to have an application, a container, you could either start with our E4S image, the big image, or you could take one of our recipes and just tweak it to just the packages that you want to install. The packages, of course, will be installed using SPAC, and then you will have a customized, compact, optimized container. The size will be considerably smaller than the one which we have, which contains a large number of packages. And then you would be able to deploy that container with one of the runtimes. Okay, right now what I showed you was that the tools and libraries were inside this full-featured super container. Your application and binaries and data was external to the containers, but you could mount those directories and run it. In the second case, when you are using the optimized builds, you might consider pointing to our mirror when we have that, and then just doing a SPAC install of that package with just the packages that you need, put your application and data and everything into a compact container, and then run it using one of our base images. So this allows you to get a feel for what SPAC and E4S can provide. And I would like to thank the Exascale Computing Project for sponsoring our work here. Any questions about E4S? Okay. Well, we have the detailed example over here on using Frontera Attack. Please follow these steps yourself. You all have access to the login information, and you should be able to try these examples and just go to the Singularity prompt and look around and see which packages are available, and maybe there are some packages that you use yourself, whether it's HDF5 or NetCDF or other open blast library that you could just use from within the container, build your application, and run it the same way, replacing the MPI with the system MPI. Does that sound like a good exercise for you to follow along in the afternoon? We have kept a lot of time here so that you can log into the systems on Frontera or your other systems and try SPAC yourself. And we'll, of course, give you this USB stick to install the packages locally on your laptop if you would like. So you can do that. If I understand that some people would prefer not to use USB sticks, and they can download it from the E4S.io directly. So let me know if anyone would like to install it locally, and I can help you with that. Todd, do you have something to add for hands-on sessions? And
Greg and I will be here to help people with SPAC stuff. We did log in and try to build on NC2 in Frontera, and the way that SPAC does compiler detection isn't quite complete there yet, so we can show you how to modify your compiler site YAML to get up and running. You just have to add the module for the compiler.
We got a couple questions yesterday about the Intel compiler and how it's sometimes tricky to set up, and it turns out that the way they've deployed compilers at TAC, we're going to have to do the same things we talked about for the Intel compiler for every compiler.
Yeah, so and we're looking at how we can change the compiler detection to fix that. Who's here from TAC? Okay, maybe I should talk to TAC. Sure.
But with the container environment, you already have SPAC pre-installed in your path, so you can at least try those commands, whether it is SPAC find or the location commands and others that we saw yesterday, and get a good feel for using SPAC with your other applications and data. And that helps with nailing down the environment so that you have the same environment on multiple platforms and a consistent way to build and run some of the applications using the libraries that are pre-built in this distribution. So there's some advantage to using that along with the bare native builds as well. Okay, thank you very much for your attention. I'll be here to answer any questions.